let's talk about calorimetry. Calorimetry is basically the experimental determination of Q and H. So we can determine our heat content. We can also determine our enthalpy. So the way it works is you calculate an unknown Q by making water the surroundings or the solution, but it functionally the same thing. Okay, and this works because of this idea called thermal equilibrium, which basically is that everything ends up having the same final temperature. So if I put something that's 0 degrees Celsius and something that's 100 degrees Celsius together, they'll both come to the final temperature of 50 degrees Celsius. So because of that, we can say that the Q of the surroundings is going to be equal to the negative Q of the system. So any heat that left the system gets absorbed by the surroundings. Any heat that leaves the surroundings gets absorbed by the system. So assuming we have an insulated system where you have system surroundings, then you can make a mathematical calculation this way. And in our calorimeter, water becomes the surroundings. So we've kind of isolated this system surrounding structure in a calorimeter, which you have a sort of example diagram here. And this is possible at all times because we know the heat capacity of water. That doesn't change. The heat capacity of water is 4.184 joules per gram degree Celsius. And the reason it's called calorimetry is because 1 calorie is 4.184 joules, because it takes 1 calorie of energy, 4.184 joules, to raise 1 gram of water by 1 degree Celsius. So if you're wondering, the food calorie is a capital C calorie or a kilocalorie. So it's 4,184 joules. Now, in a perfect calorimeter, we're going to assume that we don't lose any heat to the vessel, reaction vessel, or to the atmosphere. This is not reality, but if you're working problems on paper, sometimes you'll make this assumption. So in this case, the Q of the unknown thing you're looking at is equal to negative Q of the water, period. So for instance, a 35-gram piece of copper is heated to 100 degrees Celsius and placed in 100 grams of water at 20 degrees Celsius. Once it reaches thermal equilibrium, the water has a temperature of 22.48 degrees Celsius. What's the heat capacity? Okay. Well, the Q of water is going to be 4.184 times 100 times 2.48, right? So we can always calculate the Q of water. So 1,038 joules. And then the Q of copper is negative the Q of the water. So all the heat that left copper went into the water. So the C of copper is equal to the Q of copper divided by M times delta T. So the C of copper is negative 1,038 divided by 35 times negative 77.52. Now, where did I get that? Well, the 100 degrees Celsius is the initial. The 22.48, remember, everything comes to the same final temperature. So the final temperature for everything is 22.48, copper included. So that comes out to 0.383 joules per gram degree Celsius. Okay, so that's how you do like a heat capacity. Well, what about a reaction? So if you're calculating enthalpy, generally you want to convert to kilojoules and divide by the moles of product formed. So when 50 grams of 0.2 molar sodium chloride is mixed with 50 grams of 0.2 molar sodium hydroxide at 24.1 degrees Celsius, the reaction reaches a peak temperature of 25.7 degrees Celsius. What is the enthalpy in kilojoules per mole, assuming the solutions have the same density and heat capacity as pure water? That's an assumption that you're going to make. The fact of the matter is it's very, very close. Unless you're using like 10 decimal places, you wouldn't notice. So the Q of the solution, because it's not really water, but it's the Q of the solution. We're assuming the same heat capacity as water, 4.184, same density as water, so 1 gram per mole, but I'm 50 grams. So keep in mind, I mixed 50 and 50, so I have a total of 100 grams. And then delta T is 1.36, so you get 569 joules. Q of the reaction is negative Q of the solution, so negative 569 joules. And then delta H of the reaction is the Q of the reaction divided by the moles of the reaction. So if I did 50 moles of a 0.2 molar solution, that's 0.01 moles. So negative 569 joules divided by 0.01 moles gives me negative 56,900 joules per mole, which I'm going to report as negative 56.9 kilojoules per mole. So that's if a perfect calorimeter, but most of the time you're losing heat to the calorimeter because it's made of physical material and it's going to absorb heat. So in this case, your Q of your unknown is negative Q of the water plus Q of the calorimeter. So you're accounting for the heat that's lost to the calorimeter, okay? And the Q of the calorimeter is just the calorimeter constant times delta T. And so calorimeter constants will be joule per degree Celsius, and the delta T of the calorimeter is going to be the same as the delta T of water. So it's really just one tiny extra calculation you need to do. It's really not that big of a deal, but it is something you just have to be aware of. So let's do another metal. Chunk of iron, 50-gram chunk of iron is at 170.6 degrees Celsius. I dunk it in 250 grams of water at 20 degrees Celsius. It comes to thermal equilibrium, at which point the water is 23.2 degrees Celsius. The heat capacity of the calorimeter is found to be 16 joules per degree Celsius. What is the heat capacity of iron? So Q of water, again, super straightforward. Cm delta T for water, 3,347 joules. Now we also have to calculate the Q of the calorimeter, which is the calorimeter constant times delta T, so 16 times 3.2, or 51.2. And this is usually going to be the case. It's not a lot, but it is enough that you need to account for it. So the Q of iron is negative Q of water plus Q of calorimeter, so 33.47 plus 51.2, which is negative 3398.2 joules. So the C of iron is the Q of iron divided by M times delta T, so negative 3398.2 divided by 50 times negative 147.4. Again, it has the same final temperature as the water, and you get 0.461 joules per gram degree Celsius. Okay, bomb calorimetry is the equations are not different. It's just a slightly different type of calorimeter, and basically what it allows you to do is it allows you to combust things that you can use like styrofoam cups as a calorimeter, and it works really well. But if you need to burn something that might be dangerous or might be really, really hot, you use a bomb calorimeter. So basically, you put your sample in this bomb, and then it's surrounded by a metal jacket with a ton of water, and then you just do the same thing. The Q bomb is the calorimeter. Q of the calorimeter. You're just accounting for that, and it's just going to be a much larger calorimeter constant. So it's going to be a large, like 750 grams of water, and then it's like 700 joules per degree Celsius for the bomb or something like that. So it's really just a more versatile calorimeter, but the math is exactly the same. So if you see a bomb calorimeter, it's exactly the same math as any other calorimeter. But this is how they find when you look at a food package and it says, oh, it's this many calories. What they do is they basically blend it up with water so it's homogeneous, and then they burn it and see how much is the heat of water and they basically calculate that out to, okay, well, one hamburger, since this much hamburger heated water up this much, then the whole hamburger would have this many calories. So that's how they find calorie content of food, is they throw it in a bomb calorimeter and burn it. All right, so let's do some practice. So 1,500 milliliters of water is cooled from 90 degrees Celsius to 20 degrees Celsius. What's the heat lost? So we've got, so remember, density of water is 1 gram per milliliter. So 4.184 times 1,500 times 70. And it's a really big number. So it's 4. Now it's cooled, right? So it's negative 70. So it's negative 439,320, or negative 439 kilojoules. Again, water has really high heat capacity. Ammonium nitrate dissolves in water in an endothermic reaction. So this is like cold packs. This is what it is. When 3.21 grams of solid ammonium nitrate dissolves in 50 grams of water at 24.9 degrees Celsius, the water cools to 20.3 degrees Celsius. What is the delta H of the reaction? And so when you're calculating Q of the solution, you need to add the mass of the water plus the mass of the ammonium nitrate. All right, so you get 1,024 joules. So you have 3.21 grams of, Q of the reaction is negative 1024. Sorry, that's negative. It's positive 1024 joules, right? Endothermic, it's gaining heat. So you got 3.21 grams times 1 mole per 80 grams. Grams cancel. And you get 0.04 moles. So you have 1024 joules divided by 0.04 moles. Or 25,520 joules, which is 25.5 kilojoules. I guess slightly different answer depending on rounding. All right. When 3.12 grams of glucose is burned in a bomb calorimeter, the temperature of the calorimeter increases from 23.8 to 35.6 degrees Celsius. The calorimeter contains 775 grams of water. The bomb itself has a heat capacity of 893 joules per gram per degree Celsius. How much heat was produced by the combustion of the glucose sample? Okay, so so Q of the water is 4.184 times 775 times 11.8 or 38,263. And then the Q of the calorimeter is equal to 893 times 11.8. Always going to have the same delta T. So it's equal to 10,537. So you add those together. And you get 8,000 joules, or 48.8 kilojoules. Now, this is negative, but a lot of times if they say how much heat was produced, you'd say you report it as a positive heat, because the negative is not saying it's negative heat, it's saying the direction that it's going.